So number 6 tells us the probability of A, the probability of B. Part A asks, do we have enough information to compute the probability of A or B? And you can look at page 193 in the book to see the formulas, but the general formula for probability of A or B says add the two probabilities together and then subtract the intersection. Well, we weren't told the intersection, so for part A of this problem, no, we don't have enough information because there could be something we need to subtract and it wasn't told us. But if you look at part B of the problem, it says if you know the events are independent, that's 7. If you know the events are mutually exclusive, do you have enough information to compute probability of A or B? Well, if we know they're mutually exclusive, that means the probability of A and B occurring at the same time is 0. Mutually exclusive means events can't occur at the same time. So yes, in part B, now we do have enough information because we know what we're going to be subtracting here is 0. So we can go ahead and get the final answer. The probability, if they're mutually exclusive, the probability of A or B would be 70%. So for part 8, use the hint. Start there. What's the answer you get when we figure out the probability of B given A? And it gives us the formula here. So let's look that up. Plug the numbers given into the formula and you get that the probability of B given A would be 2. So this question we came up with in number 8 is wrong for some reason because you can't get a probability that is greater than 1. Probabilities have to be between 0 and 1. So let's go back and look at it. Why did we get an error when we came up with probabilities and then we just plugged them in this formula? So if you look at it, we said the probability that A and B would both occur is going to happen 40% of the time. 40%. A is going to happen and B is happening 40% of the time. Both things. But then we say the probability that A is going to happen only happens 20% of the time. How could both A and B occur 40% if A only happens 20% period? These numbers cannot be correct. You can't have the probability of A or B. B is not listed here, but A or B can't have a lower probability than the A and B probability. This should always be lower than any of the individual items. So A should be bigger than 0.40, and if we were told B, B should also be bigger than 0.40. So that's why we have an issue. That's why we get an erroneous result when we use these values to compute the probability of B given A. Part A of number 12 asks you to find the probability of no reaction, a mild reaction, and a strong reaction. And just use the numbers from the table. So the probability of no reaction, there were 470 people out of the total 1,000. So the probability that someone would have no reaction is 0.47. Mild reaction, there was 390 out of 1,000, 0.39. In a strong reaction, there's 140 people out of the 1,000, so 0.14. For part B, we have what's the probability that there's no reaction if we're only considering, if we're given that we're looking at the people who washed within 5 minutes. So just look at people who washed within 5 minutes. The chances of no reaction, there's 420 out of those 500 people. So there's an 84% chance of no reaction if you wash within 5 minutes. What's the chances of a strong reaction if you wash within 5 minutes? So out of the people who washed within 5 minutes, 20 had a strong. Out of the 500, 0.04. Part C I did here in red. What's the probability of no reaction now for the people who washed after 5 minutes? So if we're looking afters, there's 50 people with no reaction out of the 500, so 10%. And then what's the probability of strong reaction for people who washed after? And there's 120 out of the 500, which would be 24%. So comparing B to C, it looks like the chances of getting no reaction, it's pretty good if you wash 84% of the time, 84% chance of no reaction. If you don't wash, it drops down to just a 10% chance. And then what's the chances of getting a strong reaction? Not too good if you wash. So that's a positive news. If you wash, there's only a 4% chance you'll have a strong reaction. But the chances of a strong reaction are much higher if you wash after 5 minutes. So that's a little takeaway from looking at B and C. Looking at some and probabilities for part C or part D here. So the probability of no reaction and washing, just find that in the table. So no reaction and washing is right here, 420. So there's 420 people who meet that criteria out of the 1,000 total, 0.42. Probability of a mild reaction and washing, find those people in the table. There's 60 of them. Out of a total 1,000 gives you 0.06. Here's E, the probability of no reaction or a mild reaction. And to find that, you would add up the probabilities of both. And then you're supposed to subtract the intersection, but these are mutually exclusive events. So yes, they are mutually exclusive. That was part of E. I wanted you to say yes or no to that. And explain why. Why are they mutually exclusive? Well, you either have no reaction or a mild reaction. You can't have both at the same time. So a person falls into one or the other category. They can't be in both. If they have no reaction, by default, that means they don't have a mild reaction and vice versa. So the probability of no reaction, we figured that out in part A. It was 470 out of 1,000, 0.47. Mild reaction was 390 out of 1,000, 0.39. Add them together, there's nothing to subtract. Probability of no or a mild is 0.86. For part F, the answer is no, they're not independent. And I've talked about this a few minutes ago, but it's pretty clear from the numbers that the chances of getting no reaction greatly have increased if people wash within 5 minutes. Just look at the chart. There's 420 people compared to only 50 who waited to wash after. And we saw the numbers right here. If you wash, the chances of no reaction if you wash within 5 minutes is 84%. If you wait till afterwards, it's only 10%. So there is an effect of washing. It seems to be having an effect on whether you get a reaction or not. So that's the definition of independent, would be there is no effect in the probability for the one event doesn't affect the other, but washing is affecting your reaction. And just to look at the math clearly written out, the probability of no reaction was 0.47. 470 people out of the 1,000 had no reaction. And if they're independent, this should also be 0.47. The probability of no reaction when they wash should stay 0.47 because washing has no effect on the reaction or not. But this is not 0.47. So because it changes, we can say washing does have an effect on the no reaction. These are not independent. This number is different than this number. So washing must be affecting the chances of no reaction.